So hey everyone, I'm Mark. I work on PyTorch. I'm an applied AI engineer there. And thank you for joining this talk. I'm going to be talking to you about like a tool we built to make large-scale training a bit easier by using a new product we have called TorchX and Ray, which you're hopefully all familiar with. So quickly about me, like PyTorch is open source. So I spend the majority of my time on GitHub, like contributing to like PyTorch, like TorchSurf for model inferencing, TorchData for data loading, TorchX for infrastructure management, the subject of this talk, and examples and a bunch of miscellaneous stuff. So for the most part, like what I really worry about is, do people have a good time outside of Meta deploying models to production? And historically, this has been a pain point because at Meta, this is an easy problem. You write a JSON file and you click submit, and that's how you train models. But outside of like this bizarre world, people like need to write scripts. They need to set up their infrastructure. They need to set up their data, and this has historically been hard. So at a high level, this is really what TorchX is. Like TorchX is a way to run an application. By an application, I mean like your model.py on different schedulers. So like if you can imagine your infrastructure as something like maybe, I don't know, maybe it's like a bare metal machine, that's like your local host. Maybe it's Slurm, maybe it's Kubernetes, maybe it's Ray, which is the subject of this talk, right? And so at a high level here, like this is a really simple like hello world application. It's like prints something to console, so my app is just like literally a print hello world. But the benefit of this is that like usually in a lot of applications, people may have like different scheduling stacks. It's hard to get people to agree on which scheduling stack to use or just like throw away their code. And even for us at Meta, like there isn't really a charter to tell people like you should use this scheduler. And so having this kind of optionality is like really, really helpful. So the heart of the problem is this, or really the root of the problem is that research feels good. Research because you have like lots of pre-trained models. Projects have a due date, as in like when you're done, you're done. Like you just forget everything you wrote. You move on to the next like cool thing. There's not too many abstractions, or at least by abstractions I mean like human-created abstractions and tools you need to learn about. Like the domain is complex, as in like the problems you're wrestling with are hard, but it's really more a property of the problem. Like if anything, like what you're wrestling with is like, I don't know, the foundations of the universe and not necessarily like other people. Production is very different. Like production is, well, you have lots of options. If you happen to be successful, that somewhat feels worse because now you actually have to maintain and you're like subject to your like bad past decisions. You need to go learn like OS, operating systems, hardware, CUDA, optimization libraries. You're always debating like, should I have created like my own solution? Should I use a library? Should I use a service? The majority of abstractions are unintuitive. You're just like spending the majority of your time like Googling and pipelining stuff together. And if anything, instead of wrestling with the universe, you're wrestling with salespeoples and PMs. And so the problem here is like there is like a benefit to open source in that like because everything is there for you, you just like go do the thing that you need instead of like asking someone to do it, which is always going to be slower because they may not like share your same priorities. So there's this like proverb that I see is super popular, which is like bad workers like always blame their tools. Like I really hate this proverb because I feel like good workers improve their tools. And so I think historically in ops, people have been complaining like that stuff is hard. I don't like using this. Doesn't have to be this way. So the key problems like we were looking at for this project were people were telling us like we don't like setting up an infrastructure. Like I just have my model.py, I want to run it, and now like I need to go learn like how to set up an infra. I don't know how to turn things off. Submitting jobs against that infrastructure is like non-intuitive because they're not necessarily built with like machine learning in mind. You may want to get like logs or your job status, and if your logs are distributed over multiple machines, how do you even do that? And even like how do you go from like your model.py to like an actually end-to-end application? So I think the reason why open source works so well is that like the users of a product are fundamentally more aware of its limitations than the maintainers. So often like usability issues like it's my end users that understand them a lot better, and it's meritocratic. Like a lot of times, like I'll get feature requests from completely anonymous people that make like totally like valid points, whereas like in a more traditional prioritization structure, like I don't know, you need to be like a VP or something and influence the roadmap. You control your own destiny. You add your own features. You add your own helper functions. And for me personally, like what I feel is like the benefit of having infrastructure tools be open source is that like they ensure its long-term survival, as in the best open source tools aren't dependent on a single company. So even if that company like implodes for whatever reason, the community still exists and the project still evolves, and that's like the sign of a healthy open source project. So back to TorchX, right? So with TorchX, like after like talking of like a bunch of users, like the verbs we came up with to sort of describe what the majority of our users wanted to do were this. Like there was a TorchX run, which is you have your model.py, you run a script, and then you get a job ID back. And then you may want to describe this job as in what was the model.py, which Docker image was this running on, how many resources are associated with this machine, when was the job kicked off, the job status, did the job fail, did it succeed, did it segfault, and then the logs, like when you're actually trying to debug things from multiple machines, like actually like getting a grip as to like what actually happened. So I do want to acknowledge like there's sort of like a lot of people that helped like contribute to this story. So like Jean, Tristan, Alex, like Colin, Geeta, Cuke, Diamond, Amog, Jiao, Jules, and Richard like all helped like tremendously. So let's sort of get to the meat of how this actually works. So the example like we're going to cover is building a distributed training application from scratch. And so if you don't know how PyTorch distributed works, this is great. I'm just going to give you a quick crash course as to like what does it mean to make a job distributed. So the first part of the problem was setting up the infrastructure, right? And so Ray has this like really nice feature called Ray Up, where you can give it like a YAML file for a cluster. So for example, here, this is using like an M5 like instance on AWS, which are like cost-effective CPUs. It's using a deep learning like AMI, which has like a bunch of deep learning libraries pre-installed, and it's using Spot instances, which are cheaper. Personally, like I found this to be like a far easier experience than like using EKSCTL. They're fairly similar. But pretty much like after typing in AWS configure, giving my credentials, Ray Up, like the thing just works. And now I can have like a cluster with like hundreds of machines and not worry too much about maintaining it. The next part is just installing TorchX. So you want to install a TorchX, you want to install Ray, like nothing too surprising. But when it comes to actually submitting a job, this is really what the high-level structure looks like. So you're saying like TorchX run, so run a job, -s on a scheduler, in this case Ray, with a configuration of the dashboard address, like where you're submitting a job, the working directory, which is the files, like the models, like everything that you want to pass in, your requirements.txt, which is a list of dependencies you want to run, since we don't want to hard code those. And we're also passing in this interesting argument called dist.ddp, which is basically saying, oh, make this a DDP job with -j, a single replica, and 2 workers. So here we're running like a distributed job with 2 nodes. And the actual script you'd give would be like your train.py. So in this case, where like this example is using like TorchRec, which is like a new domain library we have for recommendation systems. But at a high level, this works like regardless of the kind of script you're running. Typically, like we've seen users like want to configure their jobs in like one of 2 ways. Like sometimes like people like the CLI experience. Other times people like the Python configuration. I personally like the Python configuration because I can like set it up and then other people can inherit it from it and then like add more stuff to it. But these essentially mean the same thing. The only real addition here, like to the previous CLI flags, is this like number of resources where you can constrain a certain job to have a certain number of CPU nodes, a certain number of GPU nodes, a certain like amount of RAM, which when you combine it with Ray Up is like a good way of like having like resource isolation per job without necessarily even like being too aware of like anything else. Like it's pretty much just a flag and you can get this stuff working. So this is the crash course with PyTorch distributed, and I realize like this is a long example, but there's like really 2 details that I want you to pay attention to here. The first is that when you open up the PyTorch distributed docs, you may see these terms like rank and world size, and I think these are just like terrible terms, but they're pretty much like borrowed from MPI, which is like the legacy way of doing distributed jobs. A rank basically means like my ID, like which of the nodes in like a distributed job, so let's say there's 10 nodes, so that's the world size is 10. And then if my rank is 5, that means I'm the 5th node among those 10 nodes, right? So this is pretty much how a lot of distributed training legacy works, which is each node has its own like rank and world size, which you set up with environment variables. So you would need to spin up, let's say, 10 machines, SSH into the machine, set up those environment variables, make sure the nodes can talk to each other, and then you can start training something. This is obviously a pain, and if you go to like, I don't know, like the PyTorch distributed like help docs, a lot of people are like the majority of issues are like setup issues. People just like set up their infrastructure wrong. They don't have like a good way of like shipping their infrastructure to us so I can debug it. Like I can't SSH into it and help them. So that's why like these setup scripts are really, really important. So there's a couple of options here like torch run, but TorchX like is basically like a wrapper on top of that makes this even easier. So great. So let's say, so now each node set up its own rank and world size. You want to also set up like a way for like nodes to talk to each other. So there's a couple of like communication protocols for this. There's like Glue. There's like Nickel for like NVIDIA GPUs. They're all like basically controlled by like a single like parameter flag. So you just like exchange a string and can experiment with like different like communication protocols. And the important detail here is when you look at the dist.allReduce parentheses t, what we're effectively doing here is we're trying to get all the nodes to agree to what the world size is. But the same thing would apply if you wanted to agree to, like, let's say your gradients. Instead of like reducing over like an integer, you would do like a reduction over a tensor. But the same idea applies. And if you understand this, you understand how distributed training works in PyTorch. So so all this time, like I've been talking about TorchX run, and once you say TorchX run, you would get like this like long string of a job ID, the Ray/TorchX with an IP, Ray submit. You know, we're working on making this like shorter. But at a high level, like once you have this URL, like that's basically the unique like ID that you can use to then like describe the job, get its status, and then also later get its logs. So the logs in this case will look something like this, right? So each process or like each node will basically print whatever you had in your job. And here it's going to say, well, we initialized like a process group, so like a group of processes that need to communicate with each other. So in distributed training terminology, this is called gang scheduling. You're scheduling a bunch of jobs that need to like collaborate with each other. And then you can see here there's two different like command actors that are each saying that each have their own process ID. And then once they agree on the world size, you can see that like in both of the logs. This is great because the alternative to this before was I need to actually SSH into like a given node and then like figure out like what happened here. And so I would literally, before I discovered TorchX, I would have like 4 terminals open and be SSHing into each one with like tail-f, just kind of not a great experience. So let me briefly talk about like how it works, right? Like at a high level, the way it works is you have a configuration of like the kind of job you want to have as a Python object. So we call this a component. And this component is serializable. And so given this component definition, we use like a new project called the Ray job API to submit jobs against the cluster. And then the Ray job API would run a driver script, which I will describe in a second, which if you used Ray before, it's sort of like your main function. And this main function takes care of like your resource requirements, the number of replicas you have, like the environment variables that I just talked about with the rank and world size. And then each of these processes or actors in Ray terminology would do like a Ray get to get back these logs. So this is really the picture here. The TorchX Ray scheduler here would essentially take a TorchX component, use the driver script, and then you can use this for submitting a job, getting job status. And the exact same architecture applies regardless of the kind of scheduler you're using. So if you happen to be using Kubernetes or Slurm, it's sort of the same thing. But there are some real benefits as to why I think you should probably consider the Ray one, which I'll talk about in a second. So yeah, like if you want to serialize stuff, like Python data classes are great. Essentially, they give you like a great idea of like what is the input parameter of something here. So in this case, we're calling it a Ray actor, which unfortunately TorchX also uses the actor terminology, but it means a different thing from Ray. So by actor in TorchX, we really mean like a worker or like a replica, which has like a name. It has a certain command, and then the environment variables that I talked about here, which would be, again, rank and world size are the most important ones. And then some resource requirements like number of CPUs and number of GPUs. So under the hood, this uses like the Ray job SDK. So the Ray job SDK here will take like a given like job ID. The entry point is basically what are you running when this job is first being executed. So this is the Ray driver script. And then the runtime environment, which are, again, those two famous like environment variables with rank and world size. I personally found like, because like in TorchX, like we have to be familiar with so many schedulers, like I just want to give you like some idea of like how easy it was to implement some stuff. Like for example, let's say I want to get like the job status and I want to wait for like a job to finish. Well, in Ray, like I just have like this get job status function that I give it a job ID, and then I can just like pull it in a for loop, in a while loop, and then when it succeeds or fails, I'm like, great, it finished, and that was about it. So I don't have to like wrestle with like reading Kubernetes docs or anything. I can just like write Python code. I can look at the Ray source code, and I can build stuff on top of it. And this felt really good to me. The Ray driver script essentially uses an abstraction called a command actor, which is basically saying, I want you to run this job with some extra state. By extra state, I mean like a master address and a port, for example, because when you're running a distributed job, they all need to be, like all the nodes need to be aware of what the master node is. The actual Ray driver script here looks pretty simple. So you'll see this, like this is the, like if you pay attention here near the bottom at the if I equals 0, 0. So this is called like so you can see here the programming model is the single process multiple data, because this is the same program that's running on all the nodes. But the way we get different behavior is that we do an if condition on the port, right? Like, sorry, on the rank. So if your rank is 0, that means like this is the master node and doesn't need to communicate to anyone else, but people need to communicate to it. And then once you've set up all your command actors, you basically have set up you've set up the script that you want to run on all the nodes. All the nodes are aware of what the master port and master address is, and all the nodes are aware of what their rank and the world size is. And then, once you do that, like things are really easy. It's basically you launch like these different Ray actors, and to get the result from each actor, you like run array.get. So I just want to be really clear here that this is not like a toy example that I use to simplify the code. Like this is actually what the Ray driver looks like. So you just basically check, well, like, are there any active workers? If so, like wait for the results. And if there's a result, like just get it and dereference it. So super easy. So this has been kind of really interesting for us like at Meta, because like internally, like I said, we don't necessarily use like the same kinds of schedulers that people use internally. Like you can really think of Meta as having like our own like bizarro cloud that's different from what people use in open source. But this is great for us because like if there's something that works for us and we want other people to use it, we can now literally just like change a scheduler parameter. So like same thing. So like you're like, let's say you haven't even picked an infrastructure and you want to be like, well, like let me try this Ray thing, let me try this Kubernetes thing. Well, you just change the flag. It's not like you have to go like read a book and just like learn how the configuration works every time, because the verbs we're trying to have are verbs that I would hope apply to people that are more like machine learning practitioners instead of people that like love doing infrastructure. Like I got into infrastructure to make my life easy, not to learn infrastructure, because I just like training models. So as an example to this, like was TorchX, right? So TorchX is kind of unique among like our domain libraries. So TorchX is our recommendation systems library. And the way a lot of recommender systems work is that like they aggregate like dense features and also like sparse features. Like let's say, who do you know? Like like who else do you know? Like that's like relatively sparse data. And running these is kind of tricky in open source because like you need like very large embedding tables. You need those to be sharded in some way. So now all of a sudden, like you can't just like run. It's not easy to run a hello world example. But again, with the TorchX scheduler, this was really easy, and it made it really easy for us to get like people outside of Meta to try out like TorchX, because it's like, oh hey, you use Ray, great. Like just change this flag, and you can like run this code now. So this is important because like even though like I showed you like a simple Hello World example, like which was the Hello World of distributed training, like TorchX is a lot more complex. Like TorchX has like sharding policies for like a model. It has like a C++ library for inference API. It has like a central like metrics module. But that sort of doesn't matter. Like as long as you can launch it on any scheduler, that means you can run it on all of the schedulers. And so we're hoping here to create a story where people can experiment with different schedulers and not sort of create like these like top-down mandates in a company around which scheduler you should be using. So yeah, I mean, so this is like a blog announcement that we worked on where like the case study for us was really like a proof point that you can launch jobs in a scheduler agnostic manner. In particular, the example like in this blog here like ran from a notebook. So from like within a Colab notebook, I like ran Ray up. I set up the distributed jobs. I created a whole cluster, and then I looked at the results like all from a notebook. And this was just like great for me because I felt like, hey, I'm just like in this like familiar experience, but I have like this like giga cluster at my disposal. I guess as long as you have the AWS credits for it, but it just works, right? So I hope like the key takeaway here is that you don't really have to be a scientist and an infra engineer to train large models, unless you really want to. Like if you're interested in that, like by all means, don't let me stop you. But there are like better tools to sort of make this to make this easier for you and not force you to learn about like everything to just run a job. So we talked about like distributed training, but there's sort of like I said, like any TorchX app can run now on Ray. So this includes like stuff like serving a model with TorchServe. It includes like elastic job launching, which let's say you're running a distributed job and someone like trips over one of the nodes, your whole job isn't going to collapse, which is what it would do. You can like set up hyperparameter optimization. There's metric logging. Even works with PyTorch Lightning if that's like what you're more familiar with. And yeah, like I said, thank you. Give us a star. Like I said, open source is nice. Like just if there's anything you'd like us to build, feel free to open up a rant as a GitHub issue. And I would say like already the community for me has been a good sign of like people have already started to improve the TorchX Ray scheduler in ways that I didn't think was possible. And so that's why I'm in open source. So yeah, like I said, TorchX, it's a great way to run like scheduler agnostic jobs. And okay, so I've been talking a lot about scheduler agnosticity, but like why should you use the Ray scheduler, right? And so I think the big benefit here is that one, like it's all Python, so you don't need to Google anything. You can just like look at the source code and figure out what's going on. It also means that as I was like debugging distributed jobs, I got to use like the Ray debugger, which I think is like fantastic to figure out. Like I could just like set PDB across multiple nodes and figure out what's going on as I was debugging my driver script. And it was also easy to extend. Like we actually have like a person in open source that I've never met that's like working really hard to add like elastic training support on the scheduler. Like I've never talked to them, but they just like went ahead and did it. And I think this is sort of like really the benefit of having like a library that's all Python, because if that's what your ML scientists are aware of, it's very easy for them to contribute to the infrastructure. So why should you use the TorchX Ray scheduler? Like I think the three words would be like it's Pythonic, it's like debuggable, and it's scalable. And if anything, I believe like my personal opinion is that these are probably the same reasons like why PyTorch was successful. And so I hope like I can make I hope I can make like infrastructure management a bit less painful for you. So thank you so much. I will say, like, before we take questions, if any of this was interesting to you and you're looking for a job and you don't want to go to an office, like feel free to ping us. We're hiring people that are based in US, Canada, just I guess like for tax reasons. But full-time remote is great. Like a lot of our team is distributed, so feel free to just talk to me afterwards. Thank you.
Hi, thanks for the talk. This is my first time hearing about TorchX. It seems super promising. So I come from reinforced learning research world, and my lab, we have our own internal HPC system, so we use Slurm. Now, using Ray on Slurm has not been the best experience in my personal experience. And so does TorchX make something like submitted launcher, for example, obsolete?
Which part does it make obsolete? Sorry.
So the other Slurm launcher submitted.
Yeah.
Yeah. So like I just want to understand like where does TorchX stand in kind of like the ecosystem of libraries.
Okay, yeah, that's a good question actually. So internally, even within Meta, there's a lot of people that use Slurm. It's just that they don't have the best experience with it because they need to manage the cluster, and then they'll often have like these super long, like CLI arguments. So for us, again, it's more of a language thing. But if you do happen to use both Ray and Slurm, like within your work, then you can use Ray as a scheduler. And you can have the same script and you just like change a flag, and now you can run it on your Slurm scheduler. So it gives you like the flexibility instead of trying to run Slurm on Ray or vice versa. You can just basically whoever has the capacity available, just launch it. So it's like there's going to be a pool of available compute that you're sharing like with your colleagues in a lab. And this gives you the flexibility to do so without like changing anything in your scripts, actually, not a single word.
Yeah, and then how well does it integrate with something like Hydra for config management or PyTorch Lightning because they have their own kind of abstracted away system?
Yeah, I'm not personally sure what we the story there, but pretty much like as long as you can map the configurations together, I think it's sort of like easy to do it. I think there was like a GitHub issue open. Maybe Kerman here knows about Hydra. But by all means, like if it's important to you, then I think the team can quickly build it out.
Thanks.
I think we do support basic usage of Hydra or Lightning from TorchX. It's essentially like TorchX will launch it as long as it's essentially living within the Python layer.
Yeah. Yeah, Lightning for sure. Like Lightning, we have a full example called Classy Vision there, like as our Hello World example. So yeah, it's a great one to look at.
Hi, it's a great talk, thanks. Can you talk about elastic training? Are you doing elastic training in TorchX?
Yeah, so in general, the answer to that is yes. All of the schedules work with elastic training, except Ray, that's the one where the community started contributing it. So I basically just more took of a sidekick role and let them do it. But essentially, actually, TorchX was the creator of TorchX is the same creator as Torch Elastic, just to be clear. And so a lot of the ideas are similar. And just because from our observation, it's just really difficult to deal with non-elastic training beyond a certain number of node count. It's just it feels like a must. So if you look at, for example, our Classy Vision examples on Kubernetes or Slurm, those all currently have support for elastic training.
Hi, thanks again for the talk. So I'm trying to learn more about the scope of the TorchX. So based on the presentation, it looks like it's a task orchestration to orchestrate a single distributed task on a given specific scheduler, right? So so is that the case? Like for example, this is between the scheduler and the user, the application, and basically do some kind of management about that one. So do you have any? So basically, what's the next for the TorchX, right? Is there going to be some kind of experiment concept drawing or some kind of workflow? You chain multiple jobs together, task dependency. Those are something because right now it's still within a single distributed job, right? Single distributed training job. So yeah, what's next, and what's basically the scope of that?
Yeah, so here I mostly talked about the single train.py, but for us chaining workflows is obviously sort of the way people would actually use this, as in you train a model, you pull up the artifacts, you want to serve it. This is all possible today. I just didn't have too many slides about this. But fundamentally, you can think of all of these steps as being components, and you can chain them together, and that works just fine. So in general, the question around the scope I find interesting because you're right. Depending on how you view it, the scope is sort of a bit nebulous, right? It's large, and there are lots of alternatives to do similar things. I think from our observation is that from talking to people is that if people have already invested in ecosystems where they really deeply understand how to chain workflows and the existing solutions, we actually feel like, great, just use whatever makes you comfortable. But a good chunk of our users have been giving us the feedback that like, okay, I have my train.py, how do I make it distributed? I have my train.py, how do I chain it into workflows? So again, we want more people to go to prod, and this TorchX ended up like being like a good answer for us to get users.
So the TorchX has a notion of a pipeline,
Mm-hmm.
and I think as a roadmap also we are looking to see if we can provide the notion of experiments and then integrate with other tools So yeah, repeating what I was stated before. So for if you want to like run multiple components, there's a notion of pipelines. First thing. Second thing is for the road mapping, we are considering of adding additional features such as tracking your experiments and artifacts. Yeah.
All right, well, thank you everyone for joining, really appreciate it. Yeah, if you have any more questions, feel free to ping me, and if you're looking for a job, full-time remote, work on PyTorch and Ray, please come talk to me. Thank you.